this lecture will be on broadband impedance matching network design. As in the last lecture we have pointed out that single stub, double stub matching etc., they are narrow band design scheme, but nowadays with the improvement of technology, wide bandwidth signals are coming. So, wide bandwidth systems are necessary. So, impedance matching network in microwave frequencies, they need to also increase their bandwidth. So, how to attain that bandwidth briefly we will touch upon on this lecture. So, the element by which that is done or can be done, one of the simple scheme is called quarter wave transformer. It is basically a section of a larger scheme. So, in itself it is not a broadband transformer, but with it you can achieve any broadband design, that is its importance. A quarter wave transformer is seen in this, shown in this slide. It consists of, quarter wave means the length of this is length is lambda by 4, not pi by 4. So, you have a transmission line like this and this length is lambda by 4, that is and it matches, as you see that it matches a load impedance ZL and this side the characteristic impedance. Usually characteristic impedance of transmission lines are real quantities. Load in this case it can match, that means from this side if we see, we will be seeing a this input impedance, that will be Z naught only for real ZL, but we know that if our ZL is not real, we can place an stub matching device and by single or double stub, whatever you prefer, you can come to any real load and then this impedance transformer can be used. Now, this is the mathematics of quarter wave transformer. If we write the expression for this Z in, that input impedance of a transmission line of length lambda by 4 and terminated by ZL, then Z in comes something that we equate to Z naught, and from that we solve for what is the Z naught, the quarter wave transformer characteristic impedance Z1. So, that Z1 turns out to be square root of Z naught ZL, that means you see the geometric mean of the transmission lines characteristic impedance and load impedance. So, by this you can get Z1 to be any value, and but always whether you will be able to realize a transmission line with value Z1, that is up to you, that is up to technology, manufactured technology, but any value can be attempted. So, any ZL can be put to any Z naught. So, at design frequency this match gives a good impedance match. So, reflection coefficient is 0, but problem is that if we are off a bit off from that design frequency, reflection coefficient is no more 0. So, there will be a frequency response, and this if we plot the frequency response, it will be quite narrow band and quite sharp. That means, just if we are off the frequency of the design frequency, we are not having a very good match. So, this L is lambda naught. So, we are calling this particular lambda for which we design, that means for a particular frequency and the corresponding wavelength lambda naught, that we are denoting as lambda naught. So, at other frequency there will be mismatch. Let us write an expression for that mismatch. So, you see this is the mathematics. Again, as we have seen in case of the stub matching etc., that beta L, the electric length of the transmission line, that should be expressed as a function of f. So, that we have done and written it here. The what is the reflection coefficient that we are looking at from the input port of the quarter wave transformer, that is we are calling gamma in. So, you see this is mathematics, will be easy to understand, and we are considering that we are not at a design frequency. So, f is not exactly at f naught, but others, because if it is exactly at f naught, then reflection coefficient gamma in is 0, but we are slightly off. So, we have some value that is given by this. Now, this is what is the previous expression was the complex reflection coefficient. Now, we are interested in mismatch, that is VSWR. So, that is that is a scalar quantity. So, the magnitude of the reflection coefficient is sufficient to get VSWR. That is why we take the magnitude of the reflection coefficient, and that turns to be this. Ultimately, you see that with some mathematical manipulation, it becomes some trigonometric relations. Now, we say that we are not very far away from the design frequency, that means f is quite near to f naught, and then L also is not very far from lambda naught by 4. So, the thing is theta, which is beta into L, that also is quite near to pi by 2, and so we can see that reflection coefficient near the design frequency, that has a roughly cosine variation. So, that thing is shown here, the theta versus theta. If we plot the magnitude of the reflection coefficient, you see the graph, that graph is a cosine sort of graph near that a thing. Obviously, if you are far away, it is not cosine, its exact form is given by the previous exact expression, this bottom one, that is the exact one, but it can be roughly this. Now, again as I said that you can fix up what is the maximum tolerable reflection coefficient magnitude, let us call that gamma m. So, if you put a horizontal line from that gamma m, then you see at 2 points you are getting the it is cutting that frequency response. So, roughly if you stay within that theta zone, then your transformer is within the acceptable zone. So, your impedance matching is okay. So, electrical bandwidth of your transformer we can say is delta theta, which is the design portion is pi by 2 for quarter wave transformer. So, pi by 2 minus theta m, and you see the curve is symmetrical, a cos theta curve, magnitude of cos theta is symmetrical, means that around that pi by 2 it is having equal A, that is why we have broken it into 2 into half of this thing. So, pi by 2 minus theta m is the electrical bandwidth. Now, at the two edges of those bandwidth, you have one side is theta m we are calling, another is pi minus theta m, obviously because of cos theta thing. So, that if you put, you get that value of cos theta m. So, once this is a relation that theta m and the maximum allowable magnitude of the reflection coefficient, they are related by this. So, if one is specified, generally this gamma m is specified, that what is the maximum VSWR you can tolerate, from that you can find out what is the maximum reflection coefficient you can tolerate, and then you can find what is the value of your theta m. Only thing is, generally we do not express the frequency response in terms of electrical length. So, that theta needs to be converted to f. Now, in a transmission line with transverse electromagnetic or TM line, which is a coax etc., there that relationship is linear. In a waveguide and other things, that relationship always may not be linear, but there is a definite relationship. So, based on that you can find. Here we are for a TM wave, we are finding that relationship. So, this thing I think is self explanatory. You can put those values of beta etc., and from that you see here we have finally made this part, that beta L is expressed as a f by f naught, as in the single stub case. So, now we write what is delta f by f naught from here, this manipulation. So, this is a in terms of frequency we can express this. So, based on that theta value we can put. So, that we have put here, and you see that the actual things, that the frequency response for various values of ZL Z naught, that means the source source side and load side, if they are very much separated like ZL by Z naught, ZL is 10 times Z naught, you see it is a very narrow band frequency response. So, that quarter wave transformer is very sharp here, but if you come here, that is only ZL by Z naught is 4, you have a wider bandwidth. You take any particular value here, you see that as the frequency response is less sharper, more flat, then your bandwidth is increasing. Now, this is the key idea for broadband design, that if I have the two sides, that means load side and source side impedances, they are not very far away, then I have a wider bandwidth from the same section. So, in many real cases the load and source are separate away. So, you will get a very sharp frequency response, but instead of one section, if I have multiple sections, then the whole thing can be improved, that each multiple section is seeing a smaller change of load and source impedance, and then its match will be broader. So, the overall sum total match, that will be much broader, very near to 100% bandwidth sort of thing. So, that is the idea, and that is why we see again that you see that the same mismatched transformer, there are the wave first comes, then sees a mismatch here, it is a mismatched transformer. So, some portion goes here, some portion comes here, then again this here it comes, again here it sees a mismatch. So, it comes back with a reflection coefficient gamma 3, then comes here, again here some portion comes back reflected, some portion goes here, that they are calling this gamma 1 etc. So, this one can be pictured like this, one wave coming, then some portion reflected and some portion transmitted coming here, then coming here. This is called multiple reflections. As we have seen in case of power, there are multiple reflections of power waves. Similarly, here also you see lot of reflections taking place. So, we can put our electromagnetic knowledge that everywhere we know that discontinuity in impedance, that will give rise to a reflection coefficient. Now, this conditions that gamma 2, that will be less than, because this gamma 2 is occurring at this place. Let us see the previous one. Gamma 2 is here, gamma 1 is here. So, the impedance level just opposite in these two cases, that is why gamma 2 is equal to -1, gamma 3 is this. So, and you have the voltage waves continuity. So, from that you can see this comes from the power continuity. So, from that you can do this, what is the overall reflection coefficient, that is sum of the first reflection, then the second wave going to load and coming back, then the sum of that will be going. So, multiple reflections, that comes. So, this ultimately again it comes like a infinite series, as we have seen power series. So, all these cases are the same type of thing, that waves they are going and coming back. So, if you do that, finally you will see that gamma after 2 reflections, finally you can sum that geometric series and it becomes like this. So, the thing is mainly the first reflection is very important, and also the second reflection means that one transmission going to load coming back, these two are important, others are there, but the value is falling. So, mainly these two determines the steady state value. So, multi-section matching, the design is based on this multiple reflection phenomena of waves. Reflection at each section is very small, as I said that if you can make the load and source not much different in impedance, then the reflection is very small. Also, each of the transmission line section have equal lengths, and impedances are arranged either of ascending order or descending order, meaning is that if the source is at higher impedance than load, then gradually you make that from source side, suppose there are multiple sections of this quarter wave transformer, quarter wave or any equal length transformer. So, characteristic impedance you decrease progressively. On the other hand, if source is having lower impedance and load is having higher impedance, then you gradually go on increasing the characteristic impedance of sections. And this generic equation of total reflection we already written here, you see this one. So, that just like this we can write that this will be the generic equation, and with this, so you get this is the series. Now, we also assume two more things. One is the transformer is symmetrical, symmetrical in the sense that the reflection coefficient at the two ends, the meaning is suppose I have multiple sections. So, this side is source, this side is load. Now, I have some reflection of this section, let us call them, what we say that symmetrically from these two sides, the two impedances, the two reflection coefficient, they should be same, that is called symmetrical network. This does not mean that their impedances are same, this means the reflection coefficients we make same. Similarly, this one if we call it gamma 2, this also we will call it gamma 2, and this one is odd man out. So, in a phi 1 these two are same, these two are same, this is something else, that is called the symmetrical things, gamma naught is equal to gamma n, etcetera, etcetera. But here we have said that z n's are not symmetrical, we do not mean that, because this each one depends on this minus this, that minus thing is symmetrical. So, by that you can group these two, and then it becomes a cosine series. You see this series gamma 3 its magnitude, that will be sum into n theta plus cos n minus 2 theta, etcetera. So, here you can see that this is nothing but a Fourier series. So, that means the reflection overall reflection coefficient we can express in terms of reflection coefficient of multiple sections, and that is expressed in a Fourier series. We know that any arbitrary function can be represented as sum of a Fourier series. So, we can say that if we want to synthesize any broadband frequency response of any shape, that can be achieved here, that is the guarantee of Fourier. So, any arbitrary frequency response we can synthesize. So, people have tried that we can have maximally flat, that means we have a design frequency point where we have matched, where we have now near that I will have very flat as far as possible, that type of response is called Butterworth response. Now, people have also saw that okay, I do not want very flat, because I can sustain or tolerate certain amount of mismatch. So, I can have ripples that within that zone of interest the reflection coefficient may vary, it can have ups and downs, but it should not cross a limit, and then the overall bandwidth of the impedance transformer can be increased. That is called equiripple broadest or optimum design. Now, generally Chebyshev functions are there by which this design is attempted. Then someone may say that okay, whatever this thing, but I want that when the I am rejecting, that means going out of my pass band, that means I am after my bandwidth, I want that there should be a very sharp reflection coefficient change, so that some of the signals of those frequencies are rejected. Now, those are called sharpest roll off. Various elliptical functions are there which can do that. So, all that can be synthesized by that. One of that we are showing here, others all we cannot take in this class. So, maximally flat response, this is a well known, this is a Butterworth response. Butterworth response is given like this, that the overall reflection coefficient gamma theta is A is a constant into, you know that poles of the Butterworth functions, they are on a equal circle. So, they can be in a complex plane, they can be written like 1 plus e to the power minus j 2 theta, and if you have nth order, then it is multiplied by n. Nth order Butterworth we are assuming. So, rest is mathematics just to expand, and if you find that overall response, if you maximally flat means up to nth differentiation of the reflection coefficient function, that will be 0. That means, it will be flat up to nth order. So, based on that, finally, you see that you need to determine to design this A, and how many sections you will have, that will be this n, and also what are the characteristic impedance of the multiple sections, so that you achieve this synthesized reflection coefficient. So, to determine A, what we do? We put f is equal to 0. Now, theta is the electrical length, is beta into L, beta is 2 pi by lambda. Now, if we put frequency 0, it is just hypothetically, frequency 0 means this wavelength, that is infinity. So, 2 pi by infinity, this theta also becomes 0. So, f is becoming 0 means theta 0. So, we get gamma of 0. Now, what is the meaning that theta 0, electrical length of the section 0, that means there is no transmission line, the source is directly seeing the load. When that happens, what is the reflection coefficient? The overall reflection coefficient, there are not multiple sections. Now, the source is directly giving to load. So, the reflection coefficient will be ZL minus Z naught by ZL plus Z naught. And from Butterworth response we put it, the theta is equal to 0, that gives 2 to the power n A. So, by that we can solve that A will be 2 to the power minus n ZL minus Z naught by this. Now, let us write this gamma theta as a binomial series, that means this is the binomial expansion. Now, if you just work out, this can be written like this in terms of this NCN, and these are the binomial, NCN is the binomial coefficient. So, by comparison you can find out each stage reflection coefficient. So, you can find out each stage reflection coefficient gamma n, and then gamma n can be approximated. This is a mathematics thing. So, finally, this characteristic impedance of n plus 1th section can be expressed in terms of nth section. This is a recursive relation for determining stage impedances characteristic impedance of various stages, and already we have seen that this also, that we can put a maximum value of the reflection coefficient, that gives us this expression. So, theta m is this. So, single section transform analysis, we have found delta f by f naught 2 minus 4 theta m by pi. This theta m value we can put. So, all the formulas are here, you just go through, these are self explanatory if you see the slides, and the response you get very flat like this. Okay. So, this is the Butterworth response. So, summary of this is impedance matching network is designed to achieve maximally flat response. The generic expressions we have seen. So, finally, you see that you will have to find out what are the gamma n's, and then here this is actually half of this. So, in terms of binomial coefficient, you will do. In a next lecture, we will give an example of doing this. These expressions we will use, and the fractional bandwidth like before we will calculate that what is the fractional bandwidth, that we will see that the whole game is changed, and if we go on adding more and more sections, we can achieve higher and higher bandwidth. So, 30%, 40%, 70%, 90% bandwidth, these are achievable. Only price you are paying is more number of sections, etc. And the key idea, or physically you can think of this, that we are not changing the source to load impedance at one go, gradually we are changing the impedances. So, characteristic impedance of each section is slightly higher than the, let us say, source is at lower impedance and load at higher. So, we will have to go from lower to higher. So, gradually the first section will be, its characteristic impedance is bit higher than the source, the next one slightly higher, the next one slightly higher. So, that nowhere we are generating a high reflection coefficient. So, gradually the wave is allowed to match with the, as progressively it is going, it is nowhere seeing a very high jump, that is why the reflection is low. So, more or less various frequencies they are passed easily through this transformer, that is the physical idea. I think with this we come to the conclusion, and this is the broadband MC design. So, by this whole modules we have seen that this impedance matching, what is the need, and then how to achieve that. First we have seen it by passive two-part designs, L matching that is called, then we have seen by distributed lines, that is called stubs, how to do that, and then how to improve the bandwidth, so that the impedance matching is realistic. Thank you.